Okay, it is now time to expand our treatment of conservation quantities and begin to think about a new idea, this idea of momentum. And the way that I'm going to introduce the need for this new quantity is through an example of two objects colliding. And so I've got on the left-hand side of my example here, I've got block 1 moving with some velocity to the right, and block 2 is just sitting there at rest. And the blocks collide, and after the collision, the blocks are stuck together, and they're moving to the right at some unknown velocity. And so, if we think about this in terms of energy, well, if I pick the ground here as my zero height, then none of the objects at any point are going to have any gravitational potential energy, so the total energies are just going to be kinetic. So the total energy for this situation is just the kinetic energy of 1 and 2 summed up. 2 is not moving, so the total energy at the start is just 1/2 m1 v1 squared. Now after the collision, both objects are moving, so now the total energy is 1/2 m1 plus m2, right? Both objects are moving with that same speed, v1, 2. So the question is, can I figure out what the speed is for these two objects after the collision? And the answer turns out to be no. And the answer turns out to be no because the change in the total energy of your system is equal to the work done by non-conservative forces. And in this case, I don't know. Just by the information that I'm given, I don't actually know how much work is being done by non-conservative forces during this collision, so I have no way to figure out that speed after the collision. So just using energy analysis for this particular problem, we will not be able to figure out that final speed, the post-collision speed. So what we need to know is the work done. And again, we weren't provided that information, so we need a different approach to solve this type of problem, and that approach is going to leverage momentum. So momentum is a new quantity. The momentum is defined as the mass of the object multiplied by the velocity vector of the object. And so momentum is a vector quantity, and the units are kilogram meter per second. No named unit for momentum, just kilogram meter per second. And so much in the same way as kinetic energy is a scalar characterization of motion, 1/2 mv squared, momentum is the vector characterization of motion, so mv. So very important to appreciate and understand that momentum is a vector, energy is a scalar, and it's that vector nature of momentum that's going to allow us in this case to actually answer that question about what is the velocity or what's the speed after the collision. All right, so let's get into how all of this fits together. Remember, if we wanted to change the kinetic energy of an object in energy analysis, we would think about, what's the net work done on that object? Net work done on the object corresponds to a change in kinetic energy. And remember, work is defined as the dot product of the applied force, dot product with the displacement vector, and then integrating that product over the entire path over which the object is traveling. And so much in the same way as net work gives rise to a change in kinetic energy, there's a very natural quantity that we're going to define that tells you immediately and directly how the momentum is changing. So how do we change momentum? You change the momentum by applying this J value. So J is known as the impulse or an impulse. So what is an impulse? How is it defined? Impulse is defined as the integral of the force vector, so the force you're applying, over some infinitesimal time for which that force is applied, and then you integrate over the entire time for which the force is being applied. Which, in other words, you can write as the impulse is just what's the average force that you're applying and what's the time interval over which you're applying that force. So impulse, force over some time interval, is the momentum analog to work in kinetic energy. So if we apply a force over a displacement, we're doing work. If we apply a force over a time interval, we're generating an impulse. And so one thing I just want to highlight is, remember Newton's second law, F equals ma. Well, if we swap out a for dv dt, the time derivative of velocity, move the mass inside the derivative, we get that the force, the net force on an object, is equal to the time derivative of the momentum vector. And this is just another way to rewrite Newton's second law. So F equals ma, or F equals dp dt. Okay, so we've got this new quantity momentum. We know that if we apply a force over some time interval, we're providing an impulse, and an impulse will change the momentum of an object. But we really want to get to this big, important idea here, that momentum is a conserved quantity. And so starting with this line right here, the total momentum of a closed or isolated system is conserved. Let's talk about what we mean by the total momentum. Well, the total momentum of a system, remember a system is just the collection of objects that you are keeping track of or analyzing the motion of for a given problem. The total momentum is just the sum of all of the momentum of all of the objects in your system. And so you can write this total as just the sum of all of the individual momentum. Now, the conservation of momentum, if our system is isolated or closed, then that means if you add up the total momentum at any time, you're going to get a constant value, right? That total momentum isn't going to change. Or if you think about it the way we were talking about conservation of energy, the change in momentum at any time, comparing any two times, the total change in momentum will always be zero, right? The total momentum will stay the same amount. And if your system isn't isolated or closed, what that means is that the change in momentum has to be equal to the net impulse that's been applied to the objects in your system, right? So just like with energy, is it possible to change the total energy of a system? Absolutely. Just got to do work from outside of the system. Can you change the momentum of a system? Absolutely. It just has to be an impulse from outside the system delivered to the objects in your system. All right. So since momentum is a vector, that means this equation, right, this conservation of momentum, it's actually two equations, or three if we're in three-dimensional dynamics. But the change in momentum in the x direction has to be zero. The change in the momentum in the y direction has to be zero. This is much in the same way as when we said F equals ma. That's really two expressions. F net in the x direction equals max, and F net in the y direction equals may. All right, so let's try to bring this together and use this new idea, conservation of momentum, to answer that problem that I started with. Remember, I've got block 1 moving with some velocity to the right. It's going to collide with block 2, which is at rest initially, and then afterwards the two blocks are moving together. They're stuck together. All right, so I'm going to call the moment before the collision, or at some time before the collision when the block 1 is moving, I'm going to call that A. And so I've got the mass, I'm setting the mass of the block to be 2 kilograms. The second block's going to have a 6 kilogram mass. The velocity of block 1 in state A is plus 10 meters per second, plus because it's to the right. And the velocity of the second block is 0. It's at rest to start. So my total momentum in state A is I'm just going to add up momentum of 1 and 2. Remember, momentum 2 is 0 because the velocity is 0. But momentum 1 is going to be 2 kilogram multiplied by the plus 10 meter per second. And so the total momentum at the start before the collision is plus, right? Momentum is a vector, so the vector is pointing to the right, 20 kilogram meter per second. So that is the total momentum that I started with. Now, if there are no impulses, external forces being applied to my system, then the total momentum is not going to change. And so if I look after the collision, now my system includes object 1 and 2, and so any interaction between those objects by definition is not an external force or interaction. Those are internal to my system. So after the collision, what do I know? Well, I know my velocity for block 1 and block 2 have to be the same value. They're moving together. I just don't know what that value is. So what's the total momentum after the collision? Well, again, it's just the sum of the two individual momenta. So mass 1 times the velocity of mass 1 afterwards. Mass 2 multiplied by the velocity of mass 2 afterwards. And so that just means my total momentum afterwards is 8 kilograms, right? Because both objects are moving at the same velocity. 8 kilograms multiplied by this unknown velocity. Now, conservation of momentum tells me that these two quantities have to be equal. So I'm going to set the plus 20 kilogram meter per second equal to the 8 kilogram multiplied by v1 2b. And that gives me that the velocity of the two objects that are stuck together after the collision, my velocity now is plus 2.5 meter per second. So leveraging the conservation of momentum here, we took a problem that seems kind of simple, but with energy analysis, we just can't actually determine what's happening. Using momentum analysis, we can immediately identify what the velocity of the two objects after the collision happens to be. And so this is going to be the next step in the course. Is we are going to look at different types of collisions, and we're going to examine how you need to leverage conservation of momentum and conservation of energy together to determine what happens after specific types of collisions. Okay?